Now, understanding confidence level is crucial for proper VAR implementation and interpretation. VAR can be defined at various confidence levels, typically ranging from 90% to 99.9%. The choice of confidence level depends on the application and the level of conservatism desired. Financial firms use different confidence levels to estimate VAR for different purposes. For daily risk management, 95% confidence levels are common. For regulatory capital calculations, 99% confidence levels are often required. For stress testing and extreme scenario planning, 99.9% confidence levels might be used. The 95th percentile is a common confidence level, gamma, used to calculate the probability P of value at risk. The mathematical relationship you can see here, the probability of a loss greater or equal to VAR at gamma equal 1 minus gamma, shows that the probability of losses exceeding VAR equals 1 minus the confidence level. For example, with a 95% confidence level, there is a 5% probability that losses will exceed the VAR estimate. This means that in normal market conditions, we expect losses to exceed our VAR estimate about once every 20 days. The choice of confidence level represents a trade-off between precision and conservatism. Higher confidence levels provide more conservative risk estimates, but may be less accurate for day-to-day risk management. Let's examine how different confidence levels are applied in practice and what they mean for different types of risk. In market risk management, 95% confidence levels, which represents 1 in 20 day events, or 99% confidence levels, which is a 1 in 100 day event, are typical values. These confidence levels are appropriate for market risk because market movements, while volatile, generally follow somewhat predictable statistical patterns. However, a 99.9% confidence level is considered more suitable for events that occur roughly once in 1,000th day. These extreme confidence levels are typically used for operational and credit risk, which can involve very large and very rare losses. Here's a concrete example. Suppose our VAR calculations shows a maximum loss of $1 million over a 30-day period, calculated with a 95% confidence level. This means there is a 5% probability that losses will exceed $1 million over any given 30-day period. In other words, we expect losses to exceed $1 million roughly once every 20 months under normal market conditions. This kind of clear quantitative statement about risk is exactly why VAR has become so popular. It translates complex statistical analysis into actionable business insights that management can understand and use for decision making. The example shows how VAR bridges the gap between sophisticated risk analysis and practical risk management. There are three fundamental approaches to calculating VAR, each with its own advantages and limitations. The three basic approaches are parametric, historical, and Monte Carlo simulation methods. The parametric method is widely used because of its computational efficiency. In this approach, we calculate the arithmetic mean, correlation, and standard deviation using historical information, then assume that returns follow a specific statistical distributions, typically just a normal distribution. Common implementation of the parametric method include the variance-covariance method and linear or delta normal VAR. The mathematical formulas you can see here for calculating VAR incorporates the assets weights, which are the W's, the standard deviation of each asset, which is the sigma, and the correlations rho to calculate the entire portfolio value at risk. The parametric method's main advantage is speed and simplicity. Once you have the parameters, VAR calculation is straightforward. However, it relies on the assumptions that returns follow a normal distribution, which may not always be the case, especially during periods of market stress when extreme events become more likely. The parametric approach works well for portfolios with linear risk exposures and when market conditions are relatively stable. But it may underestimate risk during periods of high volatility or when dealing with complex financial instruments. Let's examine the other two major VAR calculations approaches. The historical method is conceptually simple and intuitive. It utilizes historical market prices and rates to develop a distribution that can be used to determine future losses or profits within a given degree of confidence. Essentially, this method assumes that the future will represent the past, will look like the past, and uses actual historical data to estimate potential future losses. The main advantage of the historical method is that it doesn't make assumptions about the statistical distribution of returns. It uses the actual distribution observed in historical data. This can be particularly valuable during periods when returns don't follow normal distributions. The Monte Carlo method, also called the stochastic technique, is similar to the historical method in that it doesn't assume a specific distribution, but it involves running a large number of computer simulations on portfolios or securities to calculate potential risk or losses with a given confidence level. Monte Carlo simulations offers greater accuracy in measuring risk at various confidence levels because it can generate thousands or millions of potential scenarios, including extreme events that might not appear in limited historical data. However, Monte Carlo simulation is quite complex and requires significant computational resources and expertise to implement it properly. The quality of the results depends heavily on the quality of the underlying models used to generate the simulations. Now let's turn our attention to asset pricing models, which form the theoretical foundation for understanding how assets should be priced given their risk characteristics. Asset pricing models and theories are broadly used to describe observed market prices and provide frameworks for understanding why assets trade at particular price levels. These models serve two primary purposes. First, they help evaluate the fundamental value of an asset. And second, they help determine the appropriate expected return, which should have a close relationship with the fundamental value of the asset. Asset pricing models are essential tools used throughout the financial industry to determine fair asset prices, expected returns, and the risk associated with different assets. Without these models, it would be very difficult to make rational investment decisions or to determine whether assets are fairly valued by the market. These models provide the theoretical framework that underlies modern portfolio theory, capital budgeting decisions, and risk management practices. They help answer fundamental questions like, what return should we expect from this investment given its risk? And is this asset currently overvalued or undervalued by the market?